With Halloween being this dominant holiday of the season, we are going to dub this particular video the tricks and treats of factoring. There are several shortcuts to factoring that you're going to want to pick up. One of them is going to be mental factoring. The better you get at factoring, I'm going to ask you specifically to factor things mentally. It's going to save you a lot of steps, and you'll find it to be very simple. Save your brain for the harder stuff. The other thing we're going to look at today are the difference of squares and perfect square trinomials. So we're going to go ahead and start with the difference of squares. The difference of squares is a factoring shortcut that we're going to use quite a bit this year. So you want to really understand how this one affects binomials by looking at what it actually looks like. So the difference of squares can only be used if you recognize that you have a squared term being subtracted by a second squared term. If it is not a perfect square, then you cannot use this difference of squares. If it is not being subtracted, then you cannot use the difference of squares. So you're going to want to recognize some of your perfect squares. We'll go ahead and list a couple here so you can see what we're looking at. Probably want to go a little higher than that, but you kind of get the idea. 1 is the smallest perfect anything. It's a perfect square, perfect cube, perfect anything. 2 squared is 4, 3 squared is 9, etc., 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 etc. So please make sure you're looking at that. Once you recognize that you've got two perfect squares and they're being subtracted from each other, you can automatically write it as a minus b times a plus b. I'll show you why that's the case after we look at question number 1. Once we've done there, then you can use the difference of squares the rest of the time, no big deal. But I want to show you at least one example so you understand what's going on. I have a trinomial here. You'll notice that the x term is missing. Well, if the x term is missing, then we can rewrite it as x squared plus 0x minus 25. Then I'm going to employ that same strategy that I used in the prior video. Negative 25 goes here and 0 goes here. What two numbers multiply together make 25 and add up to 0? Well, that's negative 5 and positive 5. So then I can rewrite this as x squared minus 5, x plus 5x minus 25. Using four-term grouping, you'll notice here that I get x times x minus 5, and take out your GCF of 5 here and leave x minus 5 inside. The answer to this question is x plus 5 times x minus 5. Pretty soon we're going to get into complex conjugates and just regular conjugates, and you'll notice that the difference of squares is the key to why conjugates actually work. So now that you have this understanding and this clear picture of why the difference of squares is what it is, we're simply going to use the strategy of difference of squares conversion for the rest of these examples. 169 is 13, so I can rewrite this as 13 squared minus x squared. Well, I can write that as a squared minus b squared equals a minus b times a plus b. That means that if 13 squared is a squared, then 13 is a. So that means I'm going to write this as 13 minus x and 13 plus x. So this is the way that I would suggest to you, until you get really good at this, that you just walk through these steps in your mind. Makes it a lot easier for you. So you're going to look here, and it doesn't matter that we have a number in front of the variable here. As long as that number is a perfect square, we're good to go. So I'm going to rewrite this as 2 squared y squared minus 7 squared. I'm going to go ahead and use properties of exponents here, and I'm going to write this as 2y quantity squared minus 7 squared. I'm going to use that same strategy again. A squared minus b squared equals a minus b times a plus b. Well, if 2y squared is a squared, then 2y is a. So the first answer is 2y minus 7. The second answer is 2y plus 7. All right? At first glance, these don't have any perfect squares in them, but they do have a GCF. So I'm going to factor out that GCF first, and I get this. Now I see that perfect square has emerged, so I'm going to go ahead and write this as a squared minus b squared, where b squared is 3 squared. If a squared is x squared, then a is x. And likewise, b squared is 3 squared, b is 3. $20b squared minus 36 has a GCF of 4. So I'm going to go ahead and take that out, and I get 4 times, oh, let me pause and go back. I did not rewrite this correctly. I forgot about the GCF that I took out at the beginning. I almost made the same mistake I asked you guys not to make. So please be very mindful of whatever GCF you take out. Okay, back to this problem. I get 5b squared plus 9. There are several things wrong with this particular problem, and the reasons why I can't use the difference of squares show up in both places. The first place is that this first term, 5b squared, is not a perfect square. b squared is, for sure, but 5 is not. The second place that we have an issue is this plus sign. We have to remember that the difference of squares means that I've got to have subtraction. So that one is not something that can be simplified any further than just taking out the GCF of 4. All right, now we're going to get into those perfect square trinomials. We're going to look for patterns here. I'm going to start looking for those patterns by factoring. And we're going to start with some mental factoring here, kind of help you guys start to think why or how it is that we can get to that mental factoring more quickly. So notice here that I've got an x squared term and a 1 at the end. So that means AC is 1 and B is 2. 1 times 1 is 1, 1 plus 1 is 2. So now what I want you to start to see here is that when the value, the coefficient of the x squared term is 1, you can use mental factoring. The answer is going to be these two factor pairs right here. So it's going to be x plus 1 times x plus 1. The next thing we notice here is that this is the same thing multiplied together twice, so we can just write that using properties of exponents. That's x plus 1 squared. All right, we're going to use that x again, and we're going to put 9 here and 6 here. Since the coefficient of x squared is 1, we can use that mental factoring. Two numbers multiply together to make 9 and add up to 6 are 3 and 3. Those factor pairs become the answer. X plus 3 times x plus 3. That's the same number written twice, so that's going to be x plus 3 quantity squared. All right, one last one that has that coefficient of 1, so we're good to go on this. And it's going to be two numbers that multiply together to make 81 and add up to 18. That's 9 and 9. Those factor pairs become the answer. X, be careful here. Oops, I made a mistake. Minus x minus 9 times x minus 9. That's the same number written twice, so it's x minus 9 quantity squared. Now we're going to get over here a little bit trickier problem, or different problem. It's just not as easily mentally factorable, and that's okay. We saved this these three problems doing all that work so we could actually do this one rather easily. So 4 times 25 is 100. That's A times C. And we're doing negative 20. So that's going to be 10 and 10, both negatives there. So we'll go ahead and split that middle term, and that's going to be 4x squared minus 10x plus 25. 4-term grouping is going to reveal our solution, and that's going to be that we have a 2x, and that leaves us 2x minus 5. And then we have a negative 5 here. Remember, I need that plus sign to become a negative 1 because that first one is, so that's why I factor out that negative 5. And that's going to leave us 2x minus 5. So 2x minus 5 times 2x minus 5 is the same thing written twice. So that becomes 2x minus 5 quantity squared. At first glance, you'd say, man, I got to use those big numbers, but I don't because it's a GCF of 4. That's going to leave me y squared plus 12y plus 36. Then it becomes a very simple mental math factoring problem. Two numbers multiply together make 36, add up to 12. That's 6 and 6. Not going to forget about my GCF this time. Y plus 6 times y plus 6. That's the same thing written twice. So that's 4 times y plus 6 quantity squared. This is the exact same problem as the one above, except instead of a plus, it's going to be a minus. So there's our negative ones, and that's x minus 1 times x minus 1. Okay, now what we've got to do is we've got to reveal the pattern that we see in this particular set of problems. Once we reveal that pattern, it makes this factoring business a whole lot more simple. Okay? Let's go ahead and use this one as our pattern that we're going to try to discover. So we notice that if we take the square root of 81, we get 9. And we add 9 and 9 together, we get 18. Another way of looking at that is by saying, oh, I'm going to multiply the square root of the third term by 2. And that's going to give me my middle term there. So what we have here is if I have a plus b quantity squared, I'm going to rewrite it as a perfect square trinomial where a squared plus 2 times a times b plus b squared is my final answer. Now the place where that a times b actually shows up is right here. Notice that my number was 10, and that's a times b, which is 10. And then I get 20 when I multiply it by 2. So these perfect square trinomials are great shortcuts for you. So be able to recognize them because it will save you a whole lot of time. And the other one, of course, is a minus b quantity squared. And a squared minus 2ab plus b squared is our answer there. So what we're trying to do today, what I'm trying to give you an opportunity to do, is make factoring a little bit easier by understanding that there are shortcuts, by understanding that you can mentally factor certain problems very easily, and you can have a high amount of success in doing so. Factoring is not a difficult process. It's just something that you have to practice to become good at. So please take the time to master this so that you can make the rest of this unit and future units a lot more simple when we get to them.